Video problem 74, still using equilibrium constants. A closed system initially containing 1 times 10 to the negative third molar hydrogen and 2 times 10 to the negative third molar iodine is allowed to reach equilibrium. At equilibrium, the concentration of HI is 1.8 times 10 to the negative 7th times 10 to the negative third molar. Calculate Kc. So now I'm trying to calculate Kc. So obviously I don't know Kc. Right? When I write my equilibrium expression, this is what I have. I have HI squared all over hydrogen times iodine. And so what all do I know? I know Kc and I know HI. So I have two variables that I don't know at equilibrium. So in this case, I'm going to have to use what's called an ICE table. Right, let me show you how to set up an ICE table. Alright, so in an ICE table where I means the initial concentration, C means the change in concentration, and E means the equilibrium concentration, I put in anything over here, right here, I put anything that is in the equilibrium expression. So I'm going to put HI, I'm going to put hydrogen, and I'm going to put iodine. Okay, and now I'm going to fill in everything that I know. Alright, so I start out with 1 times 10 to the negative third molar hydrogen, so I'm going to put that in here in my initial. And I start out with 2 times 10 to the negative third molar iodine. So that's all I start out with. That means my HI is 0. Right? Now the change, there's different ways to calculate the change. We can look at something called Q, which we don't really do until AP. But here what we're going to say is we start out with some of the hydrogen iodine. We start out with 0 of the HI. Now in molarity, you can't get smaller than 0. That means this HI is going to have to go up. Right? It's going to have to increase. And it's going to increase by some amount 2x. The 2 because of the coefficient. Now that means if the products are going to increase, the reactants have to decrease. So that means hydrogen and iodine are going to go down. They're both going to go down by some amount x. Alright? Now, do I know any equilibrium concentrations? Yes. This is my equilibrium concentration for HI. So I'm going to put that in. 1.87 times 10 to the negative third. I do not know what hydrogen is, so I can say it's 1 times 10 to the negative third minus x. I do not know what my iodine is, so I'm going to say it's 2 times 10 to the negative third minus x. Now, I actually have an equation I can solve right here. Right? Because I can say, and I'll bring that on down here, I can say 0 plus 2x is equal to 1.87 times 10 to the negative third. That's the initial concentration, the change in concentration, and the equilibrium concentration. So I'm initially starting out with 0, it changes by some value 2x, and it ends at 1.87 times 10 to the negative third. So that can give me what x is. So that gives me an x value of 9.35 times 10 to the negative fourth. Okay, and let's make sure we understand what this means. What this means is this HI is starting out with an initial molarity of 0. It's going to go up by some amount 2x, right? And so we get an equilibrium concentration of 1.87 times 10 to the negative third. Now, in each case with hydrogen iodine, it's going to go down by some amount x, and these x's are the same x. I figured out what x is, so now I can plug that x back into here, and here and get the equilibrium concentration. So I can say that the, I can say that 1 times 10 to the negative third minus x is equal to the equilibrium concentration of hydrogen. Again, I know what x is, so I can say 1 times 10 to the negative third minus 9.35 times 10 to the negative fourth is equal to the concentration of hydrogen at equilibrium. So what do we get? I get a value of 6.5 times 10 to the negative fifth molarity is equal to the equilibrium concentration of hydrogen. I'm going to do the same thing with the iodine. Okay, so that was the hydrogen. Let's get the iodine over here. I have, for the iodine, 2 times 10 to the negative third minus x is equal to the equilibrium concentration of iodine. So that's 2 times 10 to the negative third minus my x, which is 9.35, times 10 to the negative fourth, and that's the concentration of iodine at equilibrium. So I get 2 times 10 to the negative third minus 9.35 times 10 to the negative fourth, and I get a value of 1.07 times 10 to the negative third. That's the molarity, which is the concentration of iodine. Now, let's see what we have. We know this value, because that's it right there. Right? We know this value. We just calculated that. We know this value. Just calculated that. So now it's just a matter of plugging and chugging. So let's give myself some space here. Hi squared hydrogen times the iodine. And again, those are all the equilibrium concentrations. Okay, so I get a Kc value of, I'm going to take it to 3 sig figs, 50.3. So there's an example of using an ice table. We figured out we needed the ice table when we had too many variables that we didn't know. And that's how it works in equilibrium.